Hello, everyone. Can you hear me? Okay. So my name is Gabriel Kiarie. I'm from Nyeri, Kenya. So I work at the Center for Data Science and Artificial Intelligence. That's in Dedan Kimathi University of Technology. And we'll be talking about developing low-cost open source hardware for ecosystems monitoring in the African context. So a little bit about me. So I was a 2023 Open Hardware Summit Fellow. So all along I've been wishing to attend the event physically, but I didn't manage the last two events, that's 2023, 2024, but finally 2025 I managed. Thanks to Sid for replying to my very many emails. So my background is in electrical engineering, and that's how I develop hardware. So the country in green is Kenya. It's in Eastern Africa. So about DSAIL, where I work at, it's a center in the university. And what we do is use artificial intelligence, data science to solve real world problems. And the areas we work in are ecosystems monitoring. We have health, agriculture, climate, and developing new methods. So I want to talk with you mainly about the open source hardware that we have developed for environmental monitoring. But before taking my seat, I'll also talk about a specific hardware that works with the Raspberry Pi. And I'm glad that my talk was placed at this point. That's towards the end, because I've realized there's a lot of Raspberry Pis, and I don't have to convince you that it's the Raspberry Pi is all over. So data is central to environmental conservation. So you need data to know the status of your ecosystems and the trends in them. So Africa is the one of the most biodiverse continent. And with accelerated degradation of ecosystems and loss of biodiversity, we need to up our efforts of conservation. And one of the best places to do that is in one of the most biodiverse continent. However, we have limited data. Compared to global north, we have limited data of the status of ecosystems in Africa. So what we are trying to do is try to bridge this gap. So traditionally, data was collected by conducting physical surveys. You go in the field, make observations. But that process is it requires a lot of resources. It's labor intensive. So therefore, you find that these surveys are conducted periodically with a substantial gap in between the surveys. So they are not a good way of monitoring the ecosystems. So, but with the advances in technology, we have seen development of open source boards that can be interfaced with sensors for collecting data. So using these sensors, we can collect data from our ecosystems continuously, remotely, and also even in places that are hard to access. And then we get voluminous data that we can then process. So at DSAIL, we are working towards that, and we are developing these sensors for collecting data in our ecosystems. So when you're developing hardware to deploy in the field, so there are several factors that you need to consider, because unlike in your room where you the environment is so different when you go to the field, there is a lot of factors that are different, and these include, for example, power. So mainly you get in the wild, there's no access to the grid. You have to devise ways of powering your system. So you also need, in most cases, you go for batteries. So you want your sensor to last long in the field. So you have to be to consider how the power consumption of your device. So there's cost. The ecosystems are vast, and you want to scale the deployment. So you want your system to be as cheap as possible. We have, for example, the processing capability in case you want to do edge processing. That's for real-time monitoring, and then relay the inferences. So you need to consider the processing capability of your hardware, and also things like the availability of the components that you're going to use to make your system. Now, so there are commercial hardware for monitoring ecosystems, but we opt to use locally made hardware for various reasons. For example, it's easy to customize your hardware to suit your need. And also, it's easy to, there's that ownership. You can design your hardware as you want. You don't have to depend on someone in case it fails. And also, sometimes you need licenses for the software to run the hardware. So, and generally, you find that when you design the hardware for yourself, the cost might be lower than buying the sensor. So here are the general steps that we follow when we are designing hardware at the Center for Data Science and Artificial Intelligence. So first is to analyze the requirements of the hardware. So, and that goes to the first principles. What do you want to achieve? How can you do that? Then you conceptualize the hardware after analyzing the requirements, acquire the components required to design the hardware, develop the hardware on the breadboard. That's to make sure that the system is working before you solder the components, which might be permanent, and that's irreversible. So then develop software to test the hardware. Then once the hardware is working well, proceed to design the hardware on software. Transfer design on copper clad board, perform chemical etching, place components and solder, test developed hardware, then improve the hardware if necessary, and then finally deploy the hardware to the ecosystem of interest. So here are the general steps. So we have a PCB design printed on a paper, then transferred to a copper clad board, do chemical etching, then to remove the excess copper. Then you have your tracks. Then you drill, place components, assemble the hardware, and then deploy it in the field for data collection. So there are various approaches of monitoring our ecosystems. So one way is using acoustic, that sound. We can use camera traps, and also other system for DSAIL, we have developed a bioacoustic sensor. We have a camera trap. We have river water level monitoring sensor, a stereo camera and DSAIL tree vision, an electric fence fault detector, and pi weld. So here is the bioacoustic sensor. It's a Raspberry Pi based acoustic sensor. So one approach of monitoring our ecosystems is listening. If you walk in a forest and the soundscape can tell you about the health of that ecosystem. If it's a rich soundscape, that might mean that the place is biodiverse. So what we are doing is developing acoustic sensors that will do the listening for you, and then you can do automatic classification of the species of interest. So for that case, you have something called indicator species. For us, we are working with birds. Reason being that they respond very fast to changes in ecosystems and they vocalize a lot. So that's the acoustic sensor. It's Raspberry Pi based, and to the right, it's a deployment. And the work is published. It's in the public to read and replicate the system. So the next is a camera trap. It's also Raspberry Pi based. So, and the camera trap has been deployed together with the acoustic sensor at the university's conservancy. So in my university, we have a conservancy, and there are many conservancies in Kenya. So we have deployed that for collecting image data And here are sample data that have been collected in the Conservancy. And we also, you get that these sensors collect a lot of data. Manual analysis of the data may be hard. So what we do is we develop machine learning models that are able to detect the object, that's the animal in the image, and also do the classification. So next is a river water level monitoring sensor. So the idea is to monitor our water catchment and tell how healthy they are. So, and one approach that you can do is by monitoring the water level in a river. So for example, and then you can compare that with other data sets, for example, like rainfall. If, for example, it rains and your river rises suddenly, it means there was a lot of runoff, and that could mean, for example, that there is no vegetation cover to slow down the process of runoff. So we can, in the farthest right is a graph comparing the change in water level, that's in red, and rainfall of a certain catchment. So the next is the stereo camera and DSAIL tree vision. This is a system for monitoring the development of trees. So in efforts of restoring ecosystems, one approach is planting trees. And you need to monitor the development of these trees. So what that would mean doing like physical measurement. So what we've done, and you get that these places are vast, and that would be hard to achieve. So what we've done is we have developed a stereo camera that captures an image, and then you can, from that image, you can get the height of the tree, the crown diameter, and all those parameters. And the idea is the way we humans or even other animals are able to, for example, estimate the distance to an object, and the size of the object is because we have two eyes. So from capturing, so what you're doing is replicating that and using this stereo camera. We also have developed the software for analyzing that to it's an algorithm that is able to extract those biophysical parameters from trees. So the next is an electric fence fault detector. So protected areas for wildlife mainly have electric fences, and they are usually exceptionally long. And once they get faulty, the rangers have to walk along the fence to locate the fault. So what we've done is we have developed a low-cost Raspberry Pi-based time domain reflectometry-based electric fence detector. So, and this system is placed at the beginning of the fence, and it's able to probe the fence, detect a fault, tell the location of the fault, and even the type of the fault. So, this is the last part or the last section of my presentation, and it's on PyWeld. So, various talks that have been before mine have talked about the Raspberry Pi. So, and that means that it's very common, and there are reasons why the Raspberry Pi is common. One, it's cheap. It has a high processing capability compared to basic microcontrollers. It has a wide, a global community that's active. Therefore, it's very easy to work with the Raspberry Pi. So, but it's a single board computer. So once you deploy it in the field, you need to be careful how you power it, because it's a computer. If, for example, it shuts down because the battery has get drained and there's constant writing to the storage, you might corrupt your storage and then lose all the data that you had collected. So what we've done is we have developed a power supply board to power the Raspberry Pi autonomously in the field. So with this board, we can be able to power our Raspberry Pi using a battery and a solar. And so for us in Africa, we have a lot of, especially in Kenya, the equator pass is almost at the center of the country. So we have a lot of sunshine. And we can be able to harvest solar energy to recharge our sensors in the field. So with this PyWeld, you can power your system using solar and battery. So the solar will be refilling your battery as it's being used. It also lets the user to schedule the system to operate during specific time. So unlike microcontrollers, the basic Raspberry Pi lacks the normal sleep. So, but with this system, you can be able to schedule your system to operate, for example, during a specific time of the day when you expect the phenomena you are observing to be happening. For example, when collecting bird sounds, they are mostly active in the morning hours when it's not hot. They disappear when it's hot, then come later back in the evening. So you want to save your energy not have your system running continuously. So with PyWeld, you can schedule your system to, for example, wake up in the morning, collect data, shut down. That's not so shut down. So meaning your system is not drawing any power. And then before shutting down, it's schedules to wake up later in the afternoon, and then start collecting data. And then once, for example, at night, it shuts down if your phenomenon does not happen at night, and then wake up the following day in the morning. So it also enables safe shutdown of the Raspberry Pi in case the battery gets drained. So the PyWeld enables the Raspberry Pi to monitor the battery. So the system, once it detects the cut-off voltage, it schedules to wake up later after the battery has been recharged, and then shuts down safely. So, so it also wakes up the system once the scheduled window is if it's time for the scheduled window. So, so with these features, we can be able to power your Raspberry Pi autonomously in the field. So there's a software to run the PyWeld using the Raspberry Pi. So once it wakes up, it checks if it's shut down. So also the PyWeld does set the time of the Raspberry Pi in case your data want to be time stamped. It has an onboard RTC to set the time of the Raspberry Pi. So it checks if it's shutdown time. If it's true, it sets the RTC to schedule wake up, and then the system shuts down safely. If not, it reads the battery voltage. So if the battery voltage, the voltage is above the cutoff voltage, your Raspberry Pi will continue running until the time for shutdown. If the voltage is below cutoff, the system will initiate the safe shutdown process. So here's the initial design of the PyWeld. It was called the DSAIL Power Management Board. So it was hand designed at the center and hand soldered and all that. So it was also using modules, but now we have moved to a more state-of-the-art design that if you compare for this, it was using a MOSFET-based and mechanical relay-based latching circuit, which was not stable and also consuming power, but we have moved to a MOSFET-based latching circuit that occupies less space and more stable. So the system also doesn't draw current it draws insignificant amount of current to sustain the latching circuit. Here's a comparison. When drawing from a 3.7 volt source, the new version is drawing negligible current, can be read by even the power supply. And to the right is the old version drawing 0.12 from a 3.7 volt source. And here's a comparison of the battery voltage profile of the older version. So you can see mostly for the older version, there was times it wouldn't go through the day. It would shut down midway because of the battery getting drained. So, but for the new version, you can observe that the system is, for all days, it was going through the scheduled time of operation. So you can observe there is also a trend in the curves. They start dropping because the system wakes up at 5, and then there's a rise after the sunlight and the system starts charging. So we are developing state-of-the-art hardware from the hand-soldered systems because we have since we have published our work, people read our paper and they are interested. People from the many conservancies in Kenya, they need systems to monitor ecosystems. So we are making state-of-the-art hardware so that we can provide them. So here's research in pictures for the water level monitoring system, the bioacoustic sensor, the camera trap, and the data it collects. So this is what the forest monitor data collection. And I would like to acknowledge and IDRC for funding this work. So thank you.